The paper outlines the author's approach to teaching linear algebra in a mechanized mathematical environment, emphasizing the importance of active learning and the use of computational tools such as Jupyter Notebooks, Python, and Maple. The authors argue that traditional teaching methods should be supplemented with technology to enhance student understanding and prepare them for real-world applications in fields like engineering, biology, chemistry, physics, computer science, and economics. They emphasize the need for students to learn how to use computers effectively, understand when to rely on them, and when to be suspicious of their results. The authors discuss their favorite introductory textbook, 14, which arose from an NSF-funded educational project, but note that it is not ideal for a mechanized environment. They advocate for the development of a specialized textbook tailored to teaching linear algebra in a mechanized environment, utilizing tools that students will encounter in their future careers. The paper also highlights the importance of reusing tools, as students must be trained in the use of new tools without sacrificing time spent on learning mathematical topics. The authors suggest that Jupyter Notebooks and Python are currently popular choices due to their widespread use in data science and neuroscience, although they acknowledge that the software environment for mathematics is constantly evolving. In addition to discussing the role of technology in teaching linear algebra, the authors touch on the challenges of motivating students by selecting applications that resonate with diverse interests. They mention network flow problems, electrical circuits, and Markov chains as examples of applications that might appeal to different subsets of students. The paper discusses the integration of technology in teaching linear algebra, highlighting the importance of engaging students actively. It emphasizes the analogy between recursion and mathematical induction, suggesting that learning to program in any language exercises similar mental muscles as writing a mathematical proof. The authors advocate for using technology to increase student activity, citing examples from their own experience with Python and Maple. They also discuss the white box and black box model for teaching, where students initially work without technology and later use it to reinforce their understanding. The paper outlines the need for a curriculum that includes instruction on the responsible use of new tools and assesses students on their use of technology. It concludes by highlighting the importance of using a variety of tools, including proprietary ones like Maple and Matlab, as well as free software like Python and Jupyter, to cater to different student needs and environments. In the context of teaching linear algebra, the authors emphasize the importance of utilizing modern software tools such as Python, Jupyter, and Julia to enhance student learning. Python is recognized for its support for long integer arithmetic and ease of use, while Julia is considered newer, more exciting, and promising in terms of speed and usability. The authors suggest that Python may eventually be eclipsed by Julia. The paper also highlights the role of visualization in linear algebra education. It points out that tools like Matlab's ArXiv command can provide students with an interactive experience, helping them understand eigenvalues and singular values more effectively. By allowing students to manipulate input vectors and observe the output eigenvectors and singular vectors, they gain a deeper understanding of these complex concepts. Moreover, the authors advocate for connecting equation solving and linear transformations, using 3D interactive plotting software to demonstrate how singular matrices transform a cube into a flat plane. Programming is another essential aspect of linear algebra education. The authors recommend assigning tasks that involve writing code for LU factoring, adding partial pivoting, complete pivoting, or rook pivoting. This not only helps students develop programming skills but also fosters a sense of accomplishment when they successfully complete the task. However, it is crucial to ensure that students do not cheat by copying code from online resources. Encouraging a culture of honesty and punishing those caught cheating can help maintain academic integrity. The authors also acknowledge the challenge posed by automated servers providing step-by-step solutions to math homework problems, which necessitates the need for manual work and human engagement in education. In conclusion, the paper emphasizes the significance of utilizing modern software tools, visualization, and programming in teaching linear algebra. It underscores the importance of encouraging students to engage with programming languages and develop a deeper understanding of complex concepts through interactive visualizations. The challenge posed by automated servers and the need for manual work in education are also discussed. Here is a combined summary of pages 7 and 8 of the research paper. In a modern, mechanized, first course in linear algebra, the authors emphasize the importance of topics that can be effectively taught with programming tools. 3 key topics are highlighted: the language of matrices, parametric linear algebra, and factoring matrices. The language of matrices is a crucial transition from systems of equations to matrix equations, which many mechanized systems fail to facilitate. The authors stress the importance of hand manipulation at the beginning, followed by the introduction of algebraic rules for matrix multiplication. They discuss the syntax of Matlab, Maple, and Python, highlighting the issues with transpose notation in Python. The authors explicitly teach the 4 ways of interpreting matrix multiplication, where the matrix product AB can be thought of as a collection of column vectors ABK. Technological support, such as asking students to construct the matrix on the right-hand side explicitly, can facilitate this understanding. The course also introduces complex numbers early on, which become routine with technological support. Parametric linear algebra is another essential feature, where mathematical modeling involves unknown parameters, and solutions are sought in terms of those parameters. This approach strengthens students' understanding of formulas and allows for the identification of parameters through experimental data. However, this can lead to computationally costly problems, and the authors acknowledge the significant literature on this topic. Factoring matrices is a fundamental concept in modern linear algebra, including the Turing factoring PA equals LDUR, A equals QR, and Schur factoring A equals QTQH. The authors teach factoring as a method for solving linear systems of equations and eigenvalue problems, representing a conceptual advance over Gaussian elimination. Students can factor matrices by hand, which consolidates their knowledge into a modern framework of understanding linear algebra. Elementary matrices encoding row operations, column operations, and row exchanges are also useful for teaching and reinforcing students' knowledge. In the context of teaching linear algebra, introducing block matrix manipulation and block factoring with non-commuting elements can be an effective approach. This method allows students to understand the Schur complement and the Schur determinantal formula, which is crucial for understanding the geometry of determinant and its relationship to area transformation under linear transformations. Utilizing technology such as Maple or Sage Math enables students to manipulate block matrices over non-commuting variables, providing a hands-on experience that reinforces theoretical concepts. The determinant is a pivotal concept in linear algebra, serving as a worthwhile test for linear dependence. By extending this concept using the SVD, students gain insight into data error and ill-conditioning or near-dependence. Moreover, least square solutions are essential to teach, as they help users understand and appreciate what the system has done in solving overdetermined or inconsistent problems. Eigenvalues and eigenvectors are introduced through the black box, white box approach, where computing eigenvalues by first computing the determinant of lambda ia and then solving the polynomial is considered a brute force hand computation for matrices larger than 2 times 2. Instead, using tools like ArXiv or similar, students can visualize and compute eigenvalues using technology. For instance, in Figure 2, we demonstrate how to do this using Maple. Kramer's rule, although not particularly useful computationally, has a beautiful proof that can be taught due to its elegance. This proof is appreciated by students and provides them with a deeper understanding of linear algebra. The authors discuss the importance of teaching linear algebra, particularly in the context of numerical error and data error. They emphasize the significance of the condition number, which is equivalent to the derivative, in dealing with numerical error. The computation of eigenvalues of small matrices is considered a solved problem, and eigenvalues are now viewed as answers due to the effectiveness of algorithms in practice and their global convergence in theory. The authors highlight the importance of parametric matrices, specifically in dynamical systems, which leads to bifurcation theory. They also discuss special matrices, including symmetric positive definite matrices, orthogonal matrices, triangular matrices, and others. These matrices are crucial in practice, and getting students to write programs that generate or factor them in special ways can be an interesting learning experience. The Cayley transform is also emphasized for its importance in control theory and scientific computing. The authors encourage students to invent their own kinds of matrices, such as checkerboard matrices and anti-tridiagonal matrices, which can lead to interesting developments even from bugs in their programs. Symmetric positive definite matrices are discussed in detail, highlighting their significance in practice and the importance of the Cholesky factoring for their computation. Companion matrices are also explored, which are matrix representations of multiplication by z in the ideal generated by a polynomial p, z. The authors discuss the non-uniqueness of companion matrices and the open problem of finding the best companion for a given polynomial. They also extend the idea to non-monic polynomials, leading to generalized eigenvalue problems, and discuss the use of other polynomial bases, such as Chebyshev, Bernstein, or Lagrange interpolational bases. Finally, the authors touch on the problem of finding the companion matrix with minimal height for a given polynomial, which is an open problem, and provide an example of Mandelbrot polynomials with companions of height 1, highlighting the significance of smaller height matrices in eigenvalue computation. In the context of teaching linear algebra, it is essential to incorporate proof and formal methods in the curriculum. This can be achieved by motivating students through the use of technology, such as programming assignments that encourage precise thinking and promote the understanding of proof. The development of computational skills should also be emphasized, as they are increasingly important for future careers in data science and machine learning. Assessment strategies play a critical role in determining student engagement and learning outcomes. One effective approach is to use computer-generated individual questions, which require students to work on their computers and provide full notes on their work. This method not only assesses computational competence but also promotes active learning and problem-solving skills. However, such exams can be stressful for students, and measures should be taken to alleviate this stress, such as providing practice exams ahead of time. Promoting agreement on syllabus change can be challenging, particularly when introducing new technologies and methodologies. Some colleagues and administrative structures may resist innovation due to the increased labor intensity and continuous retraining required. Nevertheless, embracing change is crucial in preparing students for a rapidly evolving field where technological advancements are constant. An example of a suboptimal linear algebra exam question is provided, highlighting the need for more relevant and challenging assessments. The question asks students to find the inverse of a given matrix, which, while doable, does not test any skills that will be necessary in their future use of linear algebra. With the advent of calculators and computers, inverting matrices by hand is no longer a practical skill. Instead, exams should focus on testing conceptual understanding, problem-solving abilities, and the application of linear algebra in real-world scenarios. Here is a combined summary of pages 15 and 16 of the research paper. The authors argue that the traditional approach to teaching linear algebra is unsatisfactory and needs to adapt to the modern technological environment. They contend that students should focus on learning to program and using mechanized mathematical tools, rather than manual computations like inverting matrices. This is because matrix factorings are more important and widely applicable in practice. The authors suggest that exam questions should be redesigned to encourage students to think about the underlying process, rather than mere arithmetic. For instance, asking students to factor a matrix into lower and upper triangular factors without pivoting can assess their understanding of the process. This approach can also be used in exams where technology is allowed, promoting critical thinking and problem-solving skills. The paper highlights the limitations of current technological platforms, which are often proprietary, unsupported, or lack standardization. The authors emphasize the importance of integrating mechanized mathematical tools into the learning process, citing the notable exception of a textbook that uses Matlab extensively. The authors believe that students should be trained to use technology, including formal methods, and to want proof and formal methods. They suggest that having students write their own programs can play a motivating and developmental role in this training. The first linear algebra course is crucial, not only because of its tools and concepts being critical for science but also as a venue for teaching the responsible use of mathematical technology. The paper concludes by referencing various works related to teaching linear algebra, including papers on global convergence of Hessenberg-shifted QR, teaching programming for mathematical scientists, and comprehensive Lie factors of polynomial matrices. The references also include works on the linear algebra curriculum, minimal height companion matrices, and parametric linear system solving.